let's say this structure. Okay. When we have this structure, we realize, even without doing anything, that this is an unstable structure. Why? Because we have two unknowns here and two unknowns here is 4. Two unknowns here and two unknowns here, total 8. But we have 3 bodies, okay, so we must satisfy 9 equations of equilibrium. So for sure, it is unstable, right? Now we said that if I didn't want to count, I just need to show you that the structure can move, and the question is how it can move, blah, blah, okay? So this is what we have talked about, right? Now, we said that the procedure to talk about stability is to try to say something about the centers of rotations. We have 3 bodies here, 1, 2, 3, right? So we need to identify, in order to show how a body can move, we need to find their centers of rotation, because we know if there is a rigid body motion, it will be about some center. Now, how do we do that? We always explore everything we know. We start exploiting anything we know about the supports, right? Because that's already immediate information. So the first things we look is at the supports, and we see here that this point doesn't move, so we say this is O1. We say here this doesn't move, so this is O3. And the next thing, so we already find the 2 centers of rotations. And then the next thing is to utilize the things we know about the connectivity between members, because for member 2 we didn't have any support, so we cannot say anything based on that. So we say based on this, we can say that the center of rotation for body 2 is this point, right? So we find O2. Now, the thing is, once you have the 3 bodies of rotation, right, in this case, as soon as I give you one piece of information about the movement, you can determine how everything else moves. For example, if I tell you that this here point moved 1 millimeter, you can find everything. What does it mean, everything? It means you can find all the rotations for all 3 bodies. You can find the horizontal, vertical motions of any point. Everything is uniquely determined, right? All right, so in this problem, give me one number, for example, this number 1, and if I have some dimensions, let's do some dimensions, let's say this is 2, let's say this is 3, let's say this is 3, let's say this is 4, some numbers, okay, doesn't matter. So as soon as I give you this number, one number, you can tell me the rotation. The rotation is 1 millimeter over 2 meters is 1/2 10 to the minus 3, right? You can find theta 1. Theta 1 here, you'll tell me immediately is 1 over 2, 10 to the minus 3, because it's 2000 millimeters, right? So once you know this point, you can tell me where this, you can figure out where exactly this point is, okay, the height of this point from geometry, right? This is 4, this is 2, so anyways, you can find from geometry where this point is. Once you know this point, I don't want to spend too much time on this, then you know exactly the coordinates of this point. You can tell me how much this rotation is, because you know this distance, so you can tell me what about this is the distance theta 2. You find theta 2, once you know theta 2, you can tell me how much, for example, this horizontal movement is. You can tell me how much this rotation. You can find everything basically, right? Once I give you something, anything, right? Any number, one single number, this number for example, or if I tell you what is the rotation here, or if I will tell you what is the rotation there, you can tell me everything, right? Everything is uniquely determined, right? We call this an unstable structure of first order. Okay, and I'm going to say that because I didn't talk about the order of stability, all right, or the degree of instability, if you want. It's unstable of order 1, right, or first degree, right? In the sense that once you give me one number, you can completely specify how everything moves, all right? Unstable of first order, and I say that also. You can see that we had 8 unknown forces. We had 9 equations of equilibrium. So we had one equation of equilibrium too much, right, to solve, right? So it became unstable of first order. Now I want to change this a little bit and show you what would happen if you have a second order instability. For example, let's say we change a little bit the structure. Okay, the same structure, okay, like this. And let's say I make this here a roller. Right? Now this is less stable than this, right? Because we relaxed even more one of the supports, right? As a matter of fact, the number of unknown reactions are 2 and 1, 3, and 2 and 2 here, total 7. But we have 9 equations of equilibrium surface, so we are missing 2 things, okay, to completely, we cannot satisfy all the equations by two, right? I mean, we are too short, right? 2 number of reactions short to satisfy all equations of equilibrium, right? Now, in this case, we say that we're going to see that if I want to talk about how this thing moves, we're going to show that specifying one number or one quantity, like for example here we could identify all the centers of rotation. We're going to show here that we cannot identify all the centers of rotation. We need to give, we missed 2 pieces of information before I can tell you how this thing moves. Let me show you how. For example, what can we say? Let's utilize everything we know. This point we know doesn't move, so we can say for sure that for body 1 the center is here. For body 3, we know that the center of rotation should lie somewhere here, but I don't know where. I do not know where. Right? So I finished. This is already, I utilized everything I know about the supports. Then I look at the connections, connectivity between body 1 and 2. I say, look, center 2 must lie somewhere here. I know that this is a common point between 2 and 3. So I know that 3, and this common point, and 2 should lie on the straight line, right? But I have, that's all I have, right? So, but I have many ways of doing that. For example, I could say that I could choose arbitrarily one of these points. For example, I could say, oh, this is here. For example, this is O3, right? And once I have this, I could tell you then O2 is here, right? And now I have 3 centers of rotation. But the way I chose this, it was arbitrary. I had an additional degree of freedom where to choose my center of rotation. That means I could have multiple centers of combinations of centers of rotation, right? All I needed is that O3 lies here, all I need that O2 lies here, and all I need is these 3 lines on one straight line, right? So it's up to me. I could do this, for example. And now, and now, basically, I specified this number C, for example, the distance C. So one number I gave you, where the center of rotation, and then I gave you, for example, also let's say this rotation delta theta, delta theta 1 or theta 1, whatever. So I need to give you 2 pieces of information, not only theta 1, because theta 1 tells me, okay, that this point here will move horizontally so much, right? It will tell me how much this will move horizontally, but it doesn't tell me anything more. Okay, I mean, I could have many ways of, because the center of rotation O2 could be anywhere on this line, right? For example, it could happen that the center of rotation was just above here. It could be here, right? O2 could be here. And if that's the case, then where is O3 in that case? If O2 will be here, then O3 on one hand lies here, on the other hand lies here. So O3 in this case is infinity. This is a possible solution. Right? I mean, I have many possibilities anywhere. I could choose O2 anywhere on this line, and then the connecting point will give me O3. So if I choose it here, then it should lie on this line and on this line. So O3 would be infinity. It means, for example, let's look this scenario. O1 here, O2 here, O3 here. Okay, let's say I tell you this moves 1 millimeter, right? Then this point here, due to the center of rotation, we have some rotation here. This will be also 1 millimeter because the distance is the same, right? Once I told you O3 is at infinity, this point here moves also 1 millimeter. Right? Vertical, this point did not move. Vertical, this point didn't move. And vertical, this point moved. If this is, let's say, 4 and this is 3, this will be 3/4. Okay? This, I found everything, right? But that's a possible solution, right? That means I had the freedom. Let's look at another one, okay? Let's say I chose my O2. Let's say I chose O2 to be on this line. Let's say I chose O2 to be here with a okay, O2 here. In that case, where is O3? O3 must lie on this line which connects O2 with this common point, so it must lie here. It must lie here. So in this case, O3 is here, right? Also a possible scenario. Let's see, if this moved 1 millimeter to the right, then this moved 1 millimeter to the right. O2 is here, right? Okay, this moved 1 millimeter to the right, this moved 1 millimeter to the right. And, okay, and this point here, this point moved, however, also vertically. That means if this rotated here, it moved also vertically, right, with this rotation. And eventually, the total displacement here will be perpendicular to this direction. This point will not move at all. Okay, so it's a scenario where this is the center of rotation. This did not move, and this moved 1 millimeter. Or this moved 1 millimeter, and this moved 1 millimeter. Or I could make this 1 millimeter, and I'm sure I can make this here 2 millimeter if I want. I have a freedom to select two of the displacements, not only one displacement. When we have a first order system, then as soon as you give me one displacement, all the other displacements are specified. Here, I have a freedom, I have a flexibility, where to put my center of rotation. Let's say, for example, let's say in this case, I'll show you that I can find a rotation. Sorry, I can find a movement. Okay, a roller here, right? I can specify, I'm claiming that I can arbitrarily give you two of the displacements. I can tell you that this is 1 millimeter, or this, okay. And I'll tell you this is 4 millimeters. Okay? Let me show you that this is possible. That means, not only one, I give you two numbers to specify the total movement. Alright? Let's do that. Okay? Center O1 is here. The rotation in this case, theta 1, is, this distance was, how much we said? 4. So it is 1/4, 10 to the minus 3. Okay? I found this distance. This here is 1 millimeter. Right? O2, I know it lies somewhere here. I don't know exactly where, but somewhere here it lies. Right? O3 lies somewhere here. Okay, O3 lies somewhere here. You agree? If this is 1 millimeter, no matter where the center of rotation is for O2, how much will this movement be? It will be also 1 millimeter. Because for this body, right, the distance from here to here is the same. So 1 millimeter here, this must be definitely 1 millimeter, otherwise this thing would extend. Right? So the question now is that I know that this is 1 millimeter and I want this to move 4 millimeters. Is that possible? Yes, it is possible. It is possible if the center of rotation is O3, right? I have to find O3. It is somewhere here, O3, but I want this point to be 1 and this to be 4. That means the distance from here to here must be 4 times bigger than the distance from here to here, right? So that means this distance from here to here in this case would be 4/3. So 4/3, so this is 4/3, this distance over this distance is 1 to 4. 4/3, 1.3, right? And then 1.3, 1.3, 1.3, this distance, and this distance is have a ratio of 1 to 4, right? So if I pick up this point here, O3 here, if my O3 is here, right? Then we are all okay. Then we have a rotation in this direction, which I can calculate. It's 1 over 4/3. So theta 3 is 1 millimeter over the distance from here to here, which is 4 over 3 meters. So it's 3/4, 10 to the minus 3. Calculate it. This displacement indeed will be this 3/4 times this total distance, which is 16 over 3 times 3/4 will give you 4. Okay, will give you the correct displacement. And once you know this, you can tell me actually that the center of rotation O2 was, this is where the center of rotation O2 is, in this case. The important thing is to understand that in this case, the structure was unstable, but it was more unstable than before. Before it was unstable, we had 1 degree of instability, right? But here, because we relaxed even more our support, we have more freedom how we can possibly move. right? Defining this rotation doesn't define the whole story here. I can find movements with different displacements here, with 0 displacement, with 1 displacement, with 4 displacement. I'll show you all these possibilities, right? Okay? So, this is the important thing, okay, that I want to talk about. For example, let's say I have a body and one pinch support. This structure is unstable, right? Of what order? First order. Why? Because we have two, from a statics point of view, right? You have two unknown reactions here, and I need to satisfy 3 equations of equilibrium, so I have, it's one time unstable, right? From a kinematics point of view now, let's see what we are saying. We are saying that as long as you tell me how one point moves, I can tell you everything about the structure. Why? Because I can tell you for sure for the structure, I can tell you, oh, one is here, right? And as long as you told me that this point, for example, this point here moved horizontally by 4 millimeters, I can tell you how everything moved, right? For example, if this distance here is 3 meters, you can tell me that the rotation was 4 over 3 times 10 to the minus 3. Okay, you can calculate the rotation. You can calculate the vertical displacement here because this rotation times this distance will give the vertical. I can find everything, right? As long as I gave you what this movement was. Or if I give you the rotation, again I can find everything, right? So you can specify one rotation and everything will follow. The second rotation, the third rotation, everything will follow. Okay, but let's say, this same example, we had here a roller, right? Now this, we have only one unknown reaction. We need to satisfy 3 equations of equilibrium. So we know already, for sure we are at least, it seems like we must be at least 2, right? As a matter of fact, we could even have 2 reactions and still be unstable of order 2. For example, I could even, if I would have another roller here, which happen to be along the same direction, right? We have 2 reactions, right? 3 equations of equilibrium. So you say, or immediately we are missing something, right? It's unstable, right? But this is unstable of order 1 or order 2. Here we have 2 reactions, 3 equations, seems like 1. But it's not 1, it is 2 in this case, right? Alright, so basically what we are saying, in this case with 1 roller, and the same case with 2 rollers, all you can tell me is what? You can tell me that the center of rotation must lie somewhere here. That's all you can tell me, right? So if you want to specify the motion, you need to tell me 2 things. First of all, pick up where your center of rotation want to be. Do you want to be here? Possible, right? And tell me how much, for example, one point will move. For example, tell me that the horizontal displacement of this point is 4 millimeters, okay? Where this distance is 1 and this distance is 2, for example. So you had the freedom to choose and this distance and one displacement. You chose 2 things before you tell me how this thing moved, right? While in this case, where we had pinch support, you just gave me 1 rotation or 1 displacement and you knew everything, right? Here, you need to give me more information because all I know is that the center of rotation lies somewhere here, but I don't know where. It could be anywhere, right? So you need 1 number to tell me where it is, and second number to tell me this, right? Or maybe you could tell me that this point horizontally moved by 2 millimeters, and let's say that this point here moved by 1 millimeter. Let's say this point moved 1 millimeter in this direction. I give you 2 pieces of information again. This information, 2 pieces of information for this system is sufficient to fully describe its motion. Why? Because, with the roller here, right? Why? Because we know that the center of the must lie here. I do not know where it is. I realize it cannot be below this level. Why? Because if it was somewhere here, then the rotation would have to be like this in order to move this to the right. But if it is moved to the right, this should move to the right. So it cannot be down here. So I already excluded where the center of rotation is. It cannot be below this line. It cannot be above this line. It cannot be above here in this example. Because if this moved like this, it means the rotation was like this, but then this would move to the left. Impossible. Right? So we realize immediately, oh, the center of rotation must be somewhere between here and here. right? Now, where should it lie? Well, it should lie closer to this and farther from this. That means the ratio of this over this must be 1 to 2. Okay? So you found exactly the center of rotation O. And once you have the center of rotation O, and you know that it's 1 millimeter, you can tell me how much the rotation is, and then you can find every other point, right? You see, so I gave you 2 pieces of information here, and with these 2 pieces of information, you could define the kinematics of this body, right? So it's unstable of order 2. Right? The same would happen in this case with the 2 rollers, right? Because all I know is that the center lies somewhere here, but I don't know where it lies. So I need to specify 2 things. How far, where exactly on this line it lies, 1 number, and then how much it rotates, 2nd number. Right? Let's say a 3rd example. Let's say I give you a body which is like this. 3, all right? This is unstable of order 3, right? Why? Because we need to satisfy 3 equations of equilibrium, basically, and we have nothing to play with, right? It's unstable of order 3. What does it mean from a kinematics point of view? That my center of rotation, I don't have any constraints. It could be anywhere. I could pick up any point, it will be center of rotation. I could pick up this point, and this is the center of rotation. So that means I could choose the x coordinate and the y coordinate of this point, already 2 points to find the center of rotation, and then tell me also what the rotation is. 3 pieces of information to fully describe the motion of this body, right? So I could tell you the x coordinate is so much, the y coordinate is so much, and this is so much, right? Or maybe I didn't give you the information about the center of rotation, but I gave you like this. Maybe I told you, look, I know that this point here, it moved somehow, but its vertical movement is, let's say, 3 millimeters. Let's say, right? I know that this point here, but I don't know exactly how it moved, because if I tell you it moved only like this, that's already 2 pieces of information. It means 3 millimeters and in this direction 0. It will be 2 pieces of information, right? But if I just tell you it moves somehow, but I know that in the vertical direction it moved 3 millimeters, that's 1 piece of information, right? If I tell you it moved only in the vertical direction, that's a different story, right? That's 2 pieces of information, because I told you this is 3 and this is 0, right? So let's see, I tell you that the vertical movement without restricting the horizontal is 3 millimeters. Let's say I tell you that this point here moved in this direction, how much? Let's say, how much? 2 mm. And let's say I told you that another point here, for example, moved something. 5 mm. Okay. Right or left? Left. Okay, so it moved left 5 mm. Okay? And let's say I put some coordinates here. So I put that this is let's say 4 meters high. This is 7 meters high. So this is at 11. Okay, this is 7 meters. Okay, I give you where this point were, right? This was at height 4. This was at height of 7. And let's say this coordinate here from here is let's say what 8, for example, right? We give this number. So I give you 3 points. I give you a body, and I tell you the point which is somewhere here at the height of 4. I don't even give. I might give you the exact horizontal position, but I might not. This point here. Okay, let's put more to the right. So let's say here, 2 millimeters. Okay. So let's say I give you these 3 points, A, B, C. I tell you these 3 points, A, B, and C. I tell you how much they move. I gave you 3 pieces of information, right? I didn't tell you this point moves only like this, maybe it moves in some other. I mean, I'll just tell you how much the horizontal rotation. These 3 pieces of information for this body, which is unstable of order 3, should be enough to tell you how everything else moves. Let's see how we deal with it, all right? Okay, we don't know the center of rotation, could be anywhere, right? Anywhere, but not quite anywhere, because if it will be, let's say, if it will be below this level, then since this point moves to the right, the rotation should be in this direction, right? If it will be somewhere here. Due to this displacement, it will move like this, right? And then this point should move also to the right. So impossible to be down there. Okay, could it be up here? Well, let's see, if it would be up here, then due to this, the rotation should be like this, but then this would move to the left. So it's impossible. So it's somewhere in between here and here, right? Okay, so it's somewhere between here and here. So then what do we say? We say, look, this movement was 5, this movement was 2. So clearly, it must be farther away from this and closer to this. So it must lie somewhere here at the point where this distance compared to this distance has a ratio of 2 to 5, right? So that means this, since this is 7, it means that we must be exactly here at 6 meters. Because at 6 meters, this distance would be 2, and this distance would be 5, right? It would lie the center of rotation. We immediately know already what its y coordinate is. It's somewhere here, right? Cannot be anywhere else, right? If it will be here in the middle, these two distances should be the same, right? Should be proportional, okay? So we know already where it lies somewhere here. Now, can we tell something about how big the rotation is? Well, of course we can, because no matter where the center is, since this is 5 millimeters, it means the rotation is first of all in this direction, and it is 5 over 5 meters is 10 to the minus 3. That's the rotation, 10 to minus 3, right? And in this direction, right? But we know that this point moved upward 3 millimeters now, right? So it means that the distance of the center of rotation from this line must be how much? Since the rotation we calculate already, 10 to the minus 3, must be 3 meters. So it means that this point here is 3 meters, it is right here. This is the center of rotation, where this distance is 3 meters. That means with these 3 pieces of information, I was able to pinpoint where the center of rotation is, and I was able to also calculate what the rotation is. So now I can go to any other point, I can tell you what any other point is, right? But I need 3 pieces of information in this case, right? Okay. Now, the 3 pieces of information, of course, should make sense. For example, if you would give me this horizontal displacement, and another horizontal displacement here, and you tell me this is 6, I'll tell you this is impossible, right? Because this 5, this 6, and this 2 is impossible, right? Because we already argued that the center of rotation between here and here, if this would be 6 here, it could not be, right? Because it would be not possible, right? Okay. So, but you need 3 pieces of information. It's unstable of order 3, this thing. So we can have different degrees of instability depending on the problem we are looking. And of course, the more rigid bodies we have, for example, if I have two rigid bodies, and let's say this is with a pin here, and I have a thing here, and this is something else like this, or this is a roller here, let's say, and I tell you how many times is this unstable, right? Let's see what we need, what we know. Okay, so this is a collection of 2 bodies. How many, in order to find exactly how this will move, how many pieces of information is to give? Okay, I know that the center of rotation O1 is somewhere here. I know this, okay? That's all I know. But I don't know where. And the other thing is that I know O1, O2, and O3 is somewhere on this. So let's see how many pieces of information we need. I need to tell you where exactly is O1. For example, I need to tell you that O1 is here. So I need to tell you this distance. So x1, that's the first number that we give. I need to give this number to find one of the centers of rotation. I know now that O2 lies somewhere on this line. So I need to tell you now how far, because again, I don't have any other constraints. So O2 could lie anywhere I want here. So I need to give you, for example, this number x2, second piece of information. And I need to tell you also, for example, how much this body rotates, theta 1. If I give you x1, x2, and theta 1, I found everything. Right? But I have freedom. I need 3 pieces of information. I tell you this to find O1, how much it will rotate, and where O2 is. Right? You need 3 pieces of information to find how this body moves. You can see that this is 1 reaction here, and 2 other forces here, 3, but we have 6 equations of equilibrium, so 6 equations with 3 unknowns, it must be unstable of order 3. Right? Now, in reality, we are going to use this instability concepts and how things move. That will be very, very important, and we're able to do very quickly the influence lines, right? We are going to talk about. Now, all the influence lines that we are going to talk about, as we're going to see, are due to unstable structures of order 1. Order 1 is the one we feel very comfortable with, right? You don't have any problem with order 1. Because order 1 means you can find all the centers of rotation, and then you can simply move something and see how everything moves, right? Right? But if you have something which is more unstable, like of order 2 or 3, or I mean, if I didn't have this would be unstable of order 4, because I could put anywhere I want. That means I could choose x1, y1 for the center of rotation here. Then I would say, okay, how far along this line? So another component, third, and then one rotation to define how everything moves. Let's do one more example, last example. So basically, I made this parenthesis to introduce you the concept of degree of instability, right? Okay, unstable, but how unstable? How much unstable? One structure can be more unstable than another. Okay, this is the point I want to make. And for example, okay, this structure is unstable, right? Can we, it's unstable because we have 2 and 1 here, 3 and 2 here, 5, 6. It's unstable at least of order 1. I just want to show me where is the centers of rotation of this structure. Two parts, part 1, part 2. Okay, so what can we say? We can say that O1 definitely is here, looking at this. We can say that O2 is definitely here, right? And we know that it should be also along this line. So that means O2 must be this point, right? O2 must be this point. It means that this body has this point which does not move, and this point doesn't move. That means body 1 is completely rigid in this case. Nothing can move. I cannot assume I have a rotation here because we have 2 centers of rotation, right? So body 1 is stable basically, and the whole instability comes from this body, which can rotate here with some rotation theta 2. Okay, so you give this theta 2, and you find that this body deformed in some way. It's unstable, right? But let's do one more time this problem with a roller here. Roller here, hinge here, another roller here. Alright? Okay, let's see what can we say in this case. In this case, we know that O1 must be somewhere along this line. Don't tell me the infinity, it could be anywhere on this line, right? I know that O2, body 2 here, body 1 here, right? O2 must lie somewhere along this line. And we know also that O1, O2, and this point must lie on a straight line. That means if I pick up, for example, O1 to be this one, let's say we picked up O1 to be this one, right? Then O2 should lie on the line which connects this with this, right? That means O2, we will know for sure it is this one in this case. No matter where, if I pick at any point, if I pick here, again it should be this, right? It means, in this case, the center of rotation, this O2 is definitely here, right? But this O2 means it doesn't move, right? That means the center of rotation, there is no movement. But we said the center of rotation is here. So it means that this again becomes a stable structure. It doesn't move at all, right? And the only thing we can have is a rotation θ2 in this case. That means again we fall in this case, right? So indeed, this structure indeed can do this. Okay, no problem. Okay, but this is only one of the solutions. There is another solution here. Okay, one more time. This, you realize, it is more unstable than this, right? So I told you that this can move like this. It is correct. It can move like this. Okay, but this is assuming that O1 is somewhere, right? What if O1? Let's take a second case. What if O1 is at infinity? What is our argument in this case? Okay, we said O1 must lie here. If I put it anywhere in a finite position, then this must be really not moving and only the right leg. But there is another possibility that O1 is at infinity here in this direction. And what do we know? We know that O2 must lie on this line because it is like this, right? And it must lie also on the line which connects this point with this. Which is the line which connects infinity with this point? What is the line which connects infinity in this direction with this point? It is this line. So it means what we are saying is that O2 must lie somewhere on this line. That means the requirement to be perpendicular to this movement and the requirement to connect infinity with this point is the same line. So it means we could not pinpoint where O2 is, right? So it means O2 could be anywhere, could be here, for example. Let's say, could be there, anywhere. So you have a freedom now to select this x, okay, this distance. Let's say, let's put some numbers here. Let's say this is 4, and this is 3, whatever, right? And let's say I chose this to be 1, let's say, right? So how is the movement in this case? In this case, what we're saying is that, look, for example, this point has center at infinity, so it does a translation. So if I tell you this is 1 millimeter, then this will be 1 millimeter, then this will be 1 millimeter, right? And if this is the center of rotation, this is 1 millimeter and this 5, this will be 5 millimeters, right? So basically the body will come here, here, and here, right? So basically what it did this type of movement, like a rotation here, but also a translation, a combination of one translation and one right? So it means in this case, in this problem, we have 2 degrees of freedom to play with. Here we had only 1. Here I only could tell you this point moved 1 millimeter or 2 millimeters or 3 millimeters. That's all. But here I can tell you how much this moved and how much this moved. For example, this moved 1, and if I tell you this moved also 1, then it means that the center of 2 was at infinity. If I tell you this moved at 2 millimeters, then it means the center of rotation was at 8 meters high, okay? It's up to us how we want to move. If I tell you the center of rotation was here, it means this point moved to the right and this moved to the left. It would also happen, right? I mean, let's say that, right? I mean, we have freedom where to place O2. If I put O2 in the middle here, it means this point didn't move. The point moved to the right 1 millimeter, the bottom point moved to the left 1 millimeter, and everything's fine. Right? We have a freedom. This is unstable of order 2, because really we have 2, 1, 2, and 2, 4 unknowns, right? And we had to satisfy 6 equations, so we had instability at least of 2, maybe more, okay? But at least 2. At least 2 means I can specify arbitrarily 2 of the numbers. And I can find centers of rotation which are consistent with this deformation, right? Okay, this is what I want to mention, okay, because actually your first homework, we have such a case, okay, where it is unstable of order 2. So you need to we specify 2 displacements, and based on the 2 displacements, you can find everything else. If I would give you only 1 displacement, you don't have a unique answer. There could be many different ways. For example, if I tell you this moved 1 millimeter, there's many ways. All this thing moved also 1 millimeter. This didn't move at all. This moved more. This moved less. Right? I mean, you have more freedom. Right? So to summarize, okay, the degree of instability is the number of independent displacements or rotations you need to specify in order to specify fully the motion of this object. Right? If only one rotation is enough, it means it is unstable of order 1. If it cannot move at all, it's not unstable, right? If you can specify 2 numbers, it's, yeah. No, I say one more time, right? We define here that a structure might be unstable, but the instability could be of different degree. One structure could be more unstable than another, right? So we introduce the concept of degree of instability or order of instability. This, I don't know if it's a formal terms in the literature. I haven't seen it actually. I tried to look it up. I didn't find anything on stability. So, anyways, but maybe they have it. Okay. So the order of instability, the degree of instability, is how many pieces of information I need to give you in order to specify uniquely how the whole structure, how every point in the structure moves. In the case of a single, if you have a instability of first order, for example, just one rotation and you found how all that, if there are multiple bodies, you know how all the other rotations uniquely, you can specify everything uniquely. So you specify one number and you give me the whole story how it moves. If it's unstable of order 2, you need to give me 2 numbers. One number is not enough. Telling me that this point here moved 1 millimeter doesn't tell the whole story, right? Because this could move 2 millimeter. It has, right? We have more. We need to specify more numbers, okay? And the numbers we need to specify, you can think about either the number of displacements or the number of information you need to specify to uniquely find the centers of rotation. For example, here you knew it's somewhere here you knew this is somewhere here, and you knew that this must lie in a straight line. So, but as long as you give me this number, you specify 1, then O2 is automatically satisfied. Right? So you need to tell me where is O1 and how much is the rotation. Then everything is solved. 2 numbers. Right? So you need not only rotation, but you can tell me also some additional information to tell me where the centers of rotation are. Right? Okay, again, for example, if I have this, and I tell you this is the, I tell you how this point is, right? And I tell you this is a pin here, and I tell you this is unstable, and you tell me what order. Let's see, you're going to tell me, oh, O1 must be definitely here, right? O2 must be definitely here, but that's all I know. So you need to tell me 2 pieces of information. You need to tell me where is O2, how far it is, up to you, right? Because there's many different ways. So you need to tell me 1 number to specify this, and then 1 rotation. Then you found everything. Because once you know this rotation, you can find this displacement. Since you know this, you can find this rotation. You can find everything after that, right? So you need 2 pieces of information to find out how every point moves, right? Okay. All right. So that was the part. Okay, this was the parenthesis. Sorry for that, but. Any questions? Is that clear? Yeah. So, in other words, when we have something which is unstable of order higher than 1, if it's order 1, it means we can find all the centers of rotation. Right? And then we just introduce 1 rotation and we found everything, right? But when it's order of higher than 1, then we cannot find exactly where all the centers of rotation, we need additional information. Depending how many additional pieces we need, the higher the degree of instability. Right? Okay, now, okay, so let's, Any question? Again, if you have any question, let me go over it now. We'll have it tutorial tomorrow anyways, okay, so. Okay. So this closes the parenthesis. We go back to what we were talking about last time, okay? So, sorry I put it back, but I think it was important because otherwise. Okay. All right. So last time we talked about the following. We said, let's consider 3 cases, okay? We said one case is the case where we have this this kind of loading. One case where we have, let's say, this kind of loading. And one case where we have this kind of loading. Right? So we considered 3 beams which had identical type of loading between these 2 points. Between these 2 points, the loading is this, let's say, uniform loading W, okay? W0, okay? So all of them W0. And we said we calculate the shear diagram for each case. The shear diagram in this case was like this. What is this W? Did I use W or Q last time? What did I use? I don't know. W or Q? What did I call this load? Q? Huh? W, okay. So W0 is say L over 2. So positive, negative. In this case, we had an upward reaction W0L. And then we had this going down. In this case, we start with 0, we're getting pushed down. And so it was like this, minus W0L2 over 2. So we had different shear diagrams. And we said, if I consider these 3 scenarios, let's say scenario A, scenario B, and scenario C, we can see that the difference within these different diagrams is each of them is a shifted version of another. For example, if I lift this up, I will get this. If I push it down, I will get this, right? If I take this and I lift it all the way up, here it will be this, okay? One is a shifted version of another. Okay, this is obvious because also of the expression. If I write the expression here, V of x in this case is the starting value minus W0x squared. Sorry, minus W0x. Okay. And here in this case it was W0L V of x minus W0x. And in this case it was V of x was minus W0x. Okay. So we see that these 3 expressions, they differ only. The linear part is the same. This part is the same. This part is exactly the same. They only differ in the constant. This is adding W0L over 2. This is adding W0L. This is not adding anything. Okay, so they differ by constant. If I take the difference of any of these 2 diagrams, the difference is the constant, right? So if one is by 5 units bigger, it will be 5 units bigger at all points. Okay. All right. The second thing we said is if I look at the moment diagram now, then the moment diagram here was looking like this. And we know the expression for m of x was the starting moment, which was 0, plus the integral of this, so plus W0 L over 2x minus W0 x squared over 2. This is the moment diagram. What is here? Here in this case, we have a moment which is W0 L squared over 2. So the moment diagram was started with negative, and then we had positive shear, so we are going in the positive direction, less and less and less, and then at the end with 0. So the moment diagram was like this. It was negative, and the expression was minus W0 L squared over 2, the starting value, plus the integral of this, plus W0 L over Lx minus W0 x squared over 2. In this case, the moment diagram, it is to show we start at 0, we start having negatives here, so we go in the negative direction. So we go like this, okay? And the expression m of x is the integral, the starting value is 0, plus the integral of this, so it's minus W0 x squared over 2. So what's the point here? The point is that in all these three cases, this term is the same. That means anything quadratic term or higher will be the same. The only differences are in the constant and the linear term. Constant and linear term. For example, here it's 0 and this. Here it is not 0, but it is this. And instead of this coefficient for x, it is W0x. Right? Sorry. W0 L over 2. X. Here, W0, sorry, L. X. Yeah. Okay, so it's W0L x, right? So the linear term here is this. W0, and here is W0L over 2, and here you don't have any linear term, right? So the two moment diagrams, right? Whenever you have the same intermediate load, the diagrams differ only in the constant and in the linear term, right? Okay? So it means, what does it mean? It means the one is of the form, so all these moment diagrams are of the form. The first value, which is the value m1, so m of x is m1, which is the starting value, right? Then plus v of 1, the shear times x, plus, then the last term is the integral, because, okay, let's see, what is the last term? What is this expression? The expression here is v of x is the starting shear of v of 1 minus the integral of w of x dx. In general, for an arbitrary w, okay, it is like this. So the difference is only what is v1. The only difference here is that here we have a shear, here we have bigger shear, here we have no shear, okay? So the only difference in all these expressions are in the term v1. This term is the same if we have the same load. Now when we do the same in the moment, the m of x from here, integrating, is the starting moment m1 plus the integral of this, so plus v1x minus the integral of this term. That is the integral of w of x dx. Okay? So all of them have the same last term. They only differ in the constant and in the shear, in the linear term. What does it mean? It means that if I take any of these two moment diagrams, if I take the difference of them, so one diagram is like this, another one is m1 prime plus v1 prime x, but the last term is the same, right? So if I take the difference, if I take, let's say this m1 of x, and this is, let's say, m1 prime of x, right? The difference of these two diagrams is what? It is m1 minus m1 prime, that is the difference of the constants, plus v1 minus v1 prime x. These terms cancel when we take the difference. That means the difference of any of these two moment diagrams, this diagram minus this, or this diagram minus this, if I take the difference, it is a straight line. Okay? That's what we're saying. It is a straight line. Alright? So, I'm going to use this now to say the following. Okay? I want to find what is the difference of this diagram minus this diagram. It is a straight line, right? This minus this is a straight line, I'm saying. Okay? So what does it mean? It means if I take this diagram and at every point I subtract these values, that means if I take minus this value, if I take all these values, I will get eventually one straight line. What I'm claiming is that this diagram that I see here would be the diagram that I get when I connect these two endpoints, and I simply hang the parabola of a simply supported beam. One more time. Okay. I argued that any shape here any of these shapes here, they differ only in the constant in the linear term. The rest is the same. It means if I take the difference, so they look like this, a little difference, constant, different linear term, but this is the same. So if I take the difference of the two, the difference of any of these two diagrams, let's say this is diagram A, this is diagram B, if I take the difference MA minus B, there will be some constant plus a linear term. This will be the difference, right? Okay, so let's see what is the difference. So it must be a straight line, the difference, right? Okay, if it's a straight line, at this point, how much is the difference? The difference of this point and this moment here is so much. At this point, the difference between this point and this point, it is so much, 0. So that means the straight line, the difference is a straight line which passes through this point and through this point. So it must be this. So the difference between the two diagrams is this line. That means if I have already these negative values and I subtract this positive value, I will end up on this straight line. If I take this value and I subtract this value here, I will end up on this straight line. Because we said the difference between the two is a straight line. And this straight line must pass through this point because the difference of this and 0 in this case is so much. The difference between this and 0, it is so much. So it is this straight line. So this straight line, when I subtract from the straight line this parabola, I get this shape. Okay, one more time. If I say, for example, here, this moment diagram, the difference of this diagram and this diagram, based on what we said, must be a straight line, right? Okay, what is the difference of this point with this point? It is so much. What is the difference of this point with this point? It is so much, because for the simply support beam, we end up at 0. So the difference must be a straight line which passes through this point, so the difference must be this line. That means that this diagram here is a straight line, right? Right? Plus a parabola. That means I hang from a straight line the parabola, because I said the difference here is a straight line. So if I take the straight line and I add the first diagram, I should get the final diagram. So what we are saying, it is very important because very often when I have a beam and this beam is, let's say, subjected to some distributed load in some interval, and if I know the value at this point, and if I know the value of the moment at this point, if I know these two moments, if I know that the moment at this point is minus 130, and this moment here is minus 260, for example, and if I know that this intensity is 10 kilonewton per meter, right? Then you can go directly and show me what this diagram looks like between here and here without doing much work, okay? So I would say this is minus 130, so plot on the top. This is minus 260, let's say, here, right? Let's say this distance here was, let's say, 8 meters, right? So from here, from this parabola, I will hang the parabola of a simple, corresponding to a simply support beam. That means what we proved here is that the difference between two diagrams, right, is a straight line connecting the two endpoints. Why connect the two endpoints? Because this moment diagram is something. The moment diagram corresponding to the simply support beam was 0, at 0 value, so minus 130 minus 0 is minus 130. Minus 260 minus 0 for this is also minus 260. So this must be a straight line. And from this straight line, we say that the difference of this diagram, I don't know what it looks like, and this diagram must be this straight line. So all I need to do is take this straight line, add the moment diagram of the first simply support beam to get the final. Right? So when I write the equation for this, the equation for this will look exactly like before. It will look m of x will be the starting value m1, in this case minus 130, plus the shear, which I will need to calculate here, b1 of x, But from there on, the rest of the part will be the same. It will be minus W0 x squared over 2. It will be this term, which is exactly the same term we had here. It will be exactly the same. They will not differ, right? Right? So the difference is only these two terms. So if I would take now, if I would think about this beam, and underneath I think about a simply supported beam with the same type of loading, right? The same type of loading here, then I will get here this parabola. So all I need to do, all I know is that the difference of this moment diagram and the parabola should be a straight line. So what I need to do, I need to take this straight line and add the parabola. Add the parabola means from these negative values, add positive values, that means go down. And so what I get is the moment diagram that I want. So in other words, it is very useful to know that whenever we see, if we know for simply supported beam a moment diagram, we can easily extrapolate what happens in a part of a structure where we know that the load between 2 points is something, okay? Let me show you how we can apply this. First of all, let's see two things that we need to know for sure. For a simply supported beam with a load of P, we should know definitely what the moment diagram looks for this. What does it look like? It looks a straight line here and a straight line here, where this value here is PL over 4. That's the moment diagram for a simply supported beam of length L, L over 2, L over 2. We know that this is P over 2, this is P over 2, right? So the moment is P over 2 times, up to this point is P over 2 times L over 2 is P L over 4. We should know that a concentric load gives a triangular moment diagram. The second thing we need to know is that when we have a simply supported beam with a uniform distributed load, if I know that we have a uniform distributed load W, right, we should know that the moment diagram is a parabola where this value is WL squared over 8. Okay, these are two formulas we need to know. If we know these two formulas, right, then if I give you some structure, if I give you a frame, for example, let's say I give you a frame here, and for example, let's say I give you this, and let's say this is 2 meters, and this is 4 meters, and this is let's say 5 meters. Okay, all right. Okay. Let's see how easy it is to construct the moment diagram for this body. Assuming we have, let's say, a load which is like this. Right? Let's say we have this, and this value is 20 kilonewton per meter. Let's solve this problem, okay? Now, the formal way is to calculate the reactions and then start drawing the moment diagrams properly, blah, 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 okay? We can do that. I'm going to do that. As a matter of fact, one of your homework is the last year's final exam problem for statics, okay? This is your homework, okay? To refresh your memory. Right. But let's say we want to do that, okay? In a fast way, I want to get a feeling what this moment, what this looks like, all right? Okay, let's look at this, okay? We have clearly 3 reactions, okay? We clearly can say that the total load here is 20 times 4, it's actually I don't like this 20, let me make it 25. No, let's make it 24. Yeah, let's make it 24 kilonewton per meter. So 24 times 4 is 96. Okay. All right, 96 kilonewton. We calculate the reactions. It's very easy to show that the reaction here will be 64 kilonewton. This reaction will be 32 kilonewton. then this reaction will be 0 because we don't have any horizontal loads. Okay, this comes simply from the fact that the distance here is in the middle, so it's 4 to 6, right? So that means this load is closer to the support 1 to 2, right? So it's distributed 2 to 1. We calculate the reactions, done. All right? Okay. Now, in this case, this is actually maybe too easy problem because here, very easy now to calculate what is the moment at this point. The moment at this point is 0, right? Because if I cut here the structure, you don't have any moment, right? You don't have equilibrium, right? So if I consider this free body diagram and I say here, let's assume we have a positive shear, we have a positive axial force, a positive bending moment, and I have this force here, and I talk the equilibrium of this, clearly this moment is 0, right? So there is no moment there. Can we see what is the moment here? If I would cut the structure here, again for the same reason, I would assume that we have this axial load, shear load, and bending moment. It is very easy to show that this bending moment must be 64 kN/m. Okay? Positive. It is a positive 64, right? It is very easy to show that the bending moment here is 0, right? Okay. Because if I cut here, I can easily calculate this, right? So I can tell you what the moment diagram looks like in this case. What does it look like? The moment diagram looks like this. Here it was 0, here it was 0, right? The values were 0, right? So it must be the same as the moment diagram of a beam, a simply supported beam, right? Which has no loading, but a simply supported beam with no loading has 0 moment diagram. So this is a straight line. Similarly, this is a straight line. There is nothing, it's 0. There is no moment diagram in this case, right? Because I said, because I know the moment here was 0 because there was a pin. I calculated the moment here is 0. So we said all we need to do is hang from these 2 points the diagram of a simply supported beam. That is hang from 0, 0, a diagram of 0. That means 0, right? Nothing, we don't have anything, right? Between here and here, here the value was 0, here the value was plus 64, so I'm going to plot on this side because it's pulling the bottom side. So it is plus 64. So I'm going to hang from these 2 points, since I know this value, I'm going to hang because the intermediate load of a simply supported beam with no load on top of it would be 0, right? So I'm going to hang 0. So this is nothing, this is finished, this must be a straight line, right? This is a straight line. Here, the moment is 0. So it means the moment diagram is whatever we have between here and here, which is a straight line. But I'm going to hang from here now, I'm going to hang the parabola corresponding to a simply supported beam of length 4 and with a load of 24 kN/m. What is the maximum moment? The maximum moment is QL squared over 8. So 24 times 4 squared over 8, that's 48. So 48 is the maximum value. The maximum in the middle, the maximum, it's not the maximum value overall, it is the value in the middle of this. We drop by 48, that means this is 64, that means this is 32. 32 and 48 makes 80. So the value, the midpoint here is 80. So it's something, it looks like this, This is your moment diagram of this beam. The moment diagram of this beam looks like this. See, one more time. Okay, what we are saying is, if I want to calculate quickly a moment diagram, not only I want to calculate quickly, but as we are going to see, it's very important, the final diagram, because if I give you this expression, you can calculate it, we can calculate the expression. Let's calculate in a minute what is the exact analytical expression of this. But what is very important is to be able to show me that this diagram is, for example, a triangle, another triangle, and a parabola. it is important to be able to decompose your moment diagram into simple shapes, as we are going to see. This will be very important in order to do certain calculations very fast. Okay? So one more time, it is important. Okay? We didn't learn maybe we didn't talk in statics about this. Okay? What we learned in statics is, if I give you this problem here, we learned how to construct sequentially. Okay, the axial diagram it's independent. We learn how to do the shear diagram, and based on the shear diagram, how to do the moment diagram. We know how to do that very well. Okay, this we know how to do. Okay, and then we can get the analytical expression. That's what is the function of the moment for each case. Okay. For example, let's do this in this case. How would we do it? How would I do it for this being? For this being, I would need to find first of all the starting values here. So I cannot talk about this being before I create a cut here and tell you what is the starting values, right? So what do? After we calculate the reactions, we assume we have positive shears, positive axial force, similarly here, positive shear and positive bending moment. We assume we have all this, okay, everything positive, and we calculate the starting values. It's very important to calculate the starting values. Okay, whenever we want to draw shear or bending moment diagram along a beam, we need to know the starting values. To do that, we analyze this. We see that there is a force 32 here going down. There is 0 moment here, and there is 0 axial force. If there is 32 here, it means there is 32 upward here, okay? The moment here is 0, and the axial force here. So we know the starting values, that's the important thing. Once we know the starting values, let's very quickly draw the diagrams now. The value is plus 32 for the shear, right? We start with plus 32. Nothing happens between here and here, so we stay constant for 2 meters, right, until this point. And then from this point, you have a force of 24 pushing you down. 24 over 4 meters means it pushes you down by 96. So you end up here at minus 64. This is the shear diagram. Right? 32 positive. And then you start getting pushed down to this, okay? That means the expressions, we have to get 2 expressions. If I call this x1 and if I call this x2, I must get separate expressions. The v of x1 is plus 32, constant, and v of x2, this value is what? 32 minus, because we start losing, 24 times x2. Okay, these are the expressions in terms of x1 and x2. Okay? And when we draw the moment diagram based on this now, we say we start with 0 moment. We have a positive shear, so we must move in a positive direction with a constant slope. Between here and here, we will add 32 times 2, we will end up at plus 64. So plus 64, right? And then after that, we still have positive shear, so we move in the positive direction. But this shear becomes smaller and smaller, so it becomes curved now. At this point here, it will become 0. After that, we start having negative things, so we start going the negative direction. And the total area we gain between here and here is the area under this diagram. The total area under this diagram. How much is this area? This area is plus 32. Minus 64 makes minus 32. The average of the 2 sides is minus 16. That means this plus this over 2 is minus 16. Minus 16 times the distance of 4 is minus 64. So from plus 64, we lose 64 and we come to 0. Okay, I calculate directly the area of this trapezoid. This is a trapezoid, not with 2 positive sides, but with 1 positive side with 1 negative side, right? The total area is the average of the 2 sides times the distance. So this is the moment diagram M of x, the moment diagram M. And if I want to write the expressions, I will write M of x1. M of x1 is the starting value 0. plus the integral of this plus 32 x1. So this is the expression from here to here. And m of x2 for this part, this is x2, this is x1. M of x2 is the starting value, which was 64, plus the integral of this, plus 32 x2 minus 12 x2 squared. This is the expression for the function of x2. But you see, this expression, it's a parabola. This indeed is a parabola. But it doesn't, I have only done, okay, with this, of course, this is very, very powerful because we can calculate at any point what happens. But if I want to calculate, for example, what happens at the distance at this point, which is 2 meters to that, if I plug in here 2, right, then I will get 64 plus 32 times 2 makes 128. 128 minus 12 times 2 squared, 12 times 4 makes 48. 128 minus 48 makes 80. It's exactly the value we found before. Right? But the nice thing here is that I know exactly that this shape can be decomposed into one triangle and one parabola. This is very, as we're going to see, it will be very, very useful later, because when we calculate statically indeterminate structures, we need to multiply diagrams. And we don't want to start doing analytical computation. I want to show you how to do it very fast, so you are 10 times faster than any of your classmates from other universities, okay? All right, so what did we say? Let's summarize a little bit what we said. I'm going to do one example where we're going to do a full beam, okay, a full frame. Okay, what we said is that if you can calculate, right? If you can calculate the moment at 2 points, then the total moment diagram is whatever you find this value, and you hang from there the diagram of a simply supported beam with the same load. Right? For example, if here I would have a load which is 96, I don't have this, but let's say I had a load of 96 instead of this distributed load, then let's say we change the picture now. We don't have this, we have 96. I change the problem, right? And I ask you, what does the moment diagram look like? Okay. First of all, if this would be 96, this reaction would look the same. This moment would look the same here. This is independent, right? So what we are saying here is that from this triangle, which is 64 here, I'm going to hang a triangle. I'm going to hang a triangle because we know we have to hang a triangle where it is 96 times 4 over 4. So I'm going to hang 96. So this value here was 32. So plus 96 will make 128. So the diagram will look like this. It will be a straight line here and like this. I calculate directly the moment diagram because I knew the value at this point. I knew the value at this point. I picked up this point because, of course, if I don't have this anymore, why not pick up this from here to here? I don't pick up from here to here because I want this to be at the midpoint. So I calculate here, right? And then I can apply, and I have a beam, simply supported beam with a load in the middle, and I just add that moment diagram to these two values. So I just calculate one value here, and then I calculate immediately this, right? Okay, we're going to do many examples. Don't worry about this if you didn't get it completely. Okay, the important thing is whenever you see whenever you have something here, some segment of beam, if you know the value of the moment here, and you know the value of the moment here, if you know that the value here of the moment is so much, and the value of this moment here is so much, if you know these values, and if you know that for a simply supported beam, if you know that for a simply supported beam of the same length, with this exactly same type of loading, if you knew the moment diagram of this, if you knew the moment diagram of this is, let's say, this, then simply you have to take this line and hang this diagram, and what you get, the total diagram of this is the straight line connecting the 1 and the 2, and then hanging from there this diagram. We hang because why? Because the difference of this diagram and this diagram must be a straight line. Right? But the difference of this diagram and this diagram at this point, since this is 0, the difference is so much. The difference at this point of this value and this value is so much. So we are talking about this straight line is the difference between this and this diagram. That means the diagram we want is the straight line plus this diagram. That's the idea. All right? Okay, we please go over your homework, and if you have any questions,